compared to what we did in the previous class. But I don't want to do that. I don't want to do a disservice, especially that was before I had taught design of experiments, and I realized how critical the F test is for design of experiments, and that's one of the, well, you can see a little box there. It's one of the things we cover in this chapter today. Is one of the reasons I decided to teach this chapter. Because originally I didn't teach this chapter because it's kind of like, well, you could read it, I think, but perhaps not. There's some nuances, especially with the F test. And so I thought, well, I need to teach that. So anyway, long way around is you may only have one class Friday. I'll let you know. But at the minimum, at least, at worst, you're going to have is two. And so, and now if my brother does teach, you need to call him Dr. Big Nerd, right? That's what he is. And I'm sure if you call him that, he will have something for you to call me the next time. Or he may, no telling what sort of embarrassing thing he might do. So I should probably provide something ahead of time.
Can we do better than Dr. Big Nerd? I mean, come on.
Oh, yeah. I mean, you can come up with other things. Whatever you want. Along those lines. Big nerd, he's pretty funny. And
Is he older or younger?
He's younger, yeah, and taller. But I'm smarter, see, so. You can tell him that. You can tell him I said that too. And then he'll say he's better looking, and he'll go on forever like that. He'll say he's a better basketball player or whatever, so yeah. We've been real close all our life. He's 6 years younger than me. But I used to include him on everything. Because I figured, hey, I got an instant, assistant, an instant teammate, and if I indoctrinate him into my style of thinking and playing, I've got an instant ally. So even though he was 6 years younger, he was always hanging around with me, and so he was always good at card games and stuff like that because he'd play with my friends, and he learned all the tricks and strategies, and so we've always been real close. He's the one I work with all the time on the legal cases and stuff. So you could ask him about that. Get him talking. You'll have fun. Ask him to tell you something. He can get off track. We won't care. We're doing well, I think. But yeah. So have we got most of us in here? Or? Yeah. All right.
The ones that care.
Yeah.
Once again.
Yeah. Okay. Well, this is chapter 10, which is the last of the chapters that that focus, we've had a series of chapters doing the t-test and doing these kind of things, and so this is the last in the series of those tests, of those chapters. Then we'll kind of switch gears and get into ANOVA and linear regression and some other things that I do think are very important. I use linear regression all the time. ANOVA shows up everywhere, and so I think those are important topics, so that's why I want to cover them. That's what we'll do in the last couple of classes. But I drew this figure, very ugly, but it doesn't matter. It's in your book. It's figure 1015, and the reason I drew it is because I love it, and I just want to call your attention to it. Sometimes there's things in a book that's really good because it really clearly shows what you go through when you think with these, and what this whole chapter, the essence of this chapter, and this is my goal, and it's in the book, like I said. But look at it, you'll see, you'll like it. But in the last chapters, we've been looking at a mean, and we've been asking questions about a mean. We made this sample, and is this mean reasonable? Does it make any sense? Or what's the confidence interval on a mean or something? We've been asking questions about one mean. The essence of this whole chapter is we're going to compare two things. We've made two samples. And you could have just used those other techniques, if you will. Like I could do a confidence interval on one mean and a confidence interval on the other and kind of look at them. And that's really essentially what this does, except they formalize it and they'll take a difference or something like that, and then they extend it just a bit. So what we're going to do, this is exactly what we'll cover today. We're going to first ask the question, do I have categorical data, where I get proportions, or do I have numerical data where I got a mean? And if it's categorical, oh my goodness, we're going to do the z-test, because we've always done the z-test, right, when it's categorical. That's my question to you last week to ponder, and I'll give you the answer when we get to the slide on there, why it's always Z. And if it's numerical, oh yeah, we've got other tests we do. And so the first question we would ask, if it's numerical, is are the samples independent? If they are not independent, you can do what's called a paired t-test. We'll cover that. If they are independent, then you've got to ask yourself, am I concerned about the mean or the variance? If I'm concerned about the mean, I've got to ask myself, do I think the standard deviations or the variance, if you will, of each of the data sets are the same? If they're the same, I didn't finish the diagram, did I? Yes, so if they're the same, you can do a pooled t-test, and if they're not the same, you can do a separate t-test. And if we're worried about variance, we'll do the f-test. And so, as I was commenting, that's one of the reasons I want to do this chapter, is to introduce this f-test over here, because this shows up all the time in your design of experiments. And so when you take that class, you'll have the f-test and the f-statistic. And so it's a disservice, I think, you can go through statistics and haven't at least seen it. And so that's one of the things we'll cover today. So that's the direction we're going. So our whole goal for today is to learn how to use these t-tests, z-tests, and now this f-test to compare two samples and to make conclusions about the mean or maybe the variance of two samples. Are they different? And so, and it may become important to whether how you took the data. And this little piece over here where you say, are the samples independent or not? They got an excellent example, two examples in fact, example 1 and example 2 in the book. And I actually did work them on Excel for you too. That watch, and in fact I'll call them out, because if you don't read the book, you might not, or don't read it carefully, you might not notice what they did. It's the same data, but they come up with two different conclusions, okay? And you say, oh gosh, darn it, I hate that. This math, we're not supposed to do that. We're not supposed to get two different answers from the same data. But two things. One is that does kind of sometimes happen in statistics, right? Because statistics is a little fuzzy. The answer isn't always 12. You got some variance in there. The other thing is they subtly had a difference in how they took the data. And, did it matter? Yeah, it mattered. The conclusion was completely different. You were able to gain more information out of the second test. And with what I would consider a subtle change in the way you collected the data. And therefore, that kind of points to the importance, the real importance of design of experiments and the way you collect your data, which we all want to think about that. Because gosh, if I can make a slight nuance, a slight tweak, and add very little cost, if you will, to my data collection, and yet make a startlingly different conclusion and gain a whole lot more information or understanding about the problem for low cost, why not do that? And so it kind of gets you thinking along those lines, sets up the perhaps gets you some interest in the design of experiments class. So again, yeah, this is ugly, but it's in the book. It's figure 1015. I guess you don't have it, I can scan it in too. I should probably do that. I meant to do that before class, and I realized I didn't, so I'll draw it. But so anyway, so that's how we're going to do two samples. We're going to compare two. We're going to wind up still using these t-tests and z-tests. So that sets your stage. Now let's see what it looks like. Now, the set of view graphs is great. They've got one example that they do a couple of different ways. Again, I like that, so that you can see the difference. But there is one mistake, and I left it in there so you can find it. And it's obvious. It's obvious. And I do that because it's kind of like, well, it's good for you also to know that, hey, books make mistakes all the time. So when you get confident with yourself and you find mistakes, don't just necessarily assume it's you, right? It could be the book. It could be the view graph. In fact, it was. So we'll see it. You'll see it. It's a glaring mistake. You'll be like, what? And I won't just let it sit up there. So yeah, we're going to do hypothesis testing and use our statistics to compare the means of perhaps two independent populations or two related populations, and we'll describe what we mean by related. Two independent populations from categorical data where we have proportions, and we may talk about the variances. And again, that does seem to sort of, it fits in the chapter because of this question over here, and you think, oh, well, it fits in and it's continuous, it makes sense to ask it. But it fits in big time in design experiments, so just remember that's coming in the future. So here, this is this laid out maybe in a different way of thinking. So we've got a bunch of two sample tests. And so if we're asking about the means and the samples are independent, say we're going to compare group 1 versus group 2, we're going to use one test. If we're asking about the means and the samples are related, say we've got the same group and we've got a before and after, some training. That's one of the examples they do. We had a group of salespeople. We see how they got, how many complaints they got. We gave them some sensitivity training, see if it improved. Okay, a before and after. Proportion from categorical data. So proportion 1 versus proportion 2. Or maybe we're concerned just about the variance. And again, that's where we get an ANOVA, analysis, the analysis of variance. So here we go. So we're going to test. First, we'll start out looking at two means. And so our goal is to test the hypothesis that there might be a difference between two population means. So you could say I want to compare mu1 to mu2, or maybe I should just subtract the two of them and compare the difference to 0. Same question, isn't it? And remember our notation again, mu, since it's a Greek letter, is referring to a population statistic, or a population parameter, and the Arabic are referring to a statistic from a sample, and the S, sample parameter population. And so we've got two possibilities, again, where the standard deviation or the variances are unknown, but assumed equal, or they're unknown and they're not assumed equal. Okay, that's good, because, well, you could be thinking that I had samples from the same thing, so they might have equal variances. Like the example that they use in these view graphs is the stock market. They've got they got the NASDAQ, or they've got two different indices. And then you think, well, they might have the same variance. They might not too. So you could see how you could have these two cases. All right, so let's see. Or we might talk about the difference between two means where the samples are independent. All right, that's where we're at. Let's see. So we can have unrelated, or they're just independent. They're selected from one population where they have no effect on each other. So that's how you could be independent. So let's see. We still got sigma 1 and sigma 2 unknown but assumed equal. We're going to use the pooled variance. So that was our picture from before. So if we don't know our two standard deviations, but we assume they're equal, we can kind of pool them together and have a simpler test called the pooled variance t-test. And if they're unknown, but we assume that they're unequal, then we'll hang on to the S1 and S2, which is the standard deviation from the sample, and use a separate variance t-test. So our approach is the same. If we've got two means from independent samples, and we want to compare the two means, we'll use a t-test. The question is, you can see we use a t-test, right? So we've gone through here, we've got independent samples, and we want to compare the means. We're going to use a t-test. And the question is, do we use a separate t-test or a pooled t-test? And the decision is use the pooled if you think that you can pool their variances. They can't have the same variances. Use the separate if you cannot. So let's look and see what these are. And again, what are our hypotheses? It's probably good to review this since we just kind of covered it last week. Remember, we sometimes will ask, are the means equal? And that was a two-tailed test because it could be off on either side. Or we might have one less than the other, which would be you're looking at, we move it over so you worry about the upper side when you're up on the high side. Or if you want one is bigger, then your rejections are when you fell in the lower side. Remember, that just comes from which way we're moving on our little distribution. And we've got to remember you reject when you're out here, and remember your thoughts on rejection was, well, I reject when we had the one sample. You're rejecting when the mean fell out there because it's just unlikely that it got out there. If I really thought my mean was here, or in this case, if I really think that mu1 minus mu2 is 0. And it falls out here or out here, that's kind of unlikely. So that's why we reject the hypothesis. Or if we're going one way or the other, if we think it's lower and it falls out here, if we think it's upper and it falls in there, it just seems unlikely. So that's why we're using two-tailed tests or one-tailed tests. And remember, 2 is a point of review, and I'll point this out in the view graphs. When we used a two-tailed test, we put alpha over 2 in each side. And we talked about, when you talked about I want an alpha percent confidence, 5%, 10%. And if we did a one-tailed test, we just stuffed all of the alpha into one side. And that's just a matter of understanding and discussion. You know, that's when people say, you know, I'm doing a 5% uncertainty or 5% confidence interval and it's a two-tailed thing, then that they know, well, half of it's on either side. If I say I'm 5%, it's a one-tail, well, I crammed all the 5% in one side. Okay, so just remember that. And well, it'll show up again. In fact, oh well, I didn't even think about it. See, here it is. Right. So yeah. So the lower tail test, you crammed all the alpha over there. The upper tails, you crammed all the alpha here. The two tails, you put each in each half. This is just a review of what we were doing before, but it's good. It's good since it's the first thing. And remember, you rejected if it fell in there for the lower tail, fell in here for the upper, fell in either one. Yeah, for the two tail. And we'll go through it in examples. All right, so now let's see. So now we're still looking at the two means, okay? And now we are assuming they're equal. Okay, we're assuming not the means, but that the variances are equal. And we've got independent samples, so let's see. So hey, they're randomly independently drawn. Yeah, our populations are normal. We have to always have that assumption for these tests to work. Or if the populations that we're sampling from are not normally distributed, then remember we had to take at least 30 samples to let the central limit theorem kick in. And where did the 30 come from? Because remember that one figure in chapter 7, I think, that had you had a random, uniform distribution, probably the worst, most unnormal one you could get. But after we took 30 samples and looked at the distribution of the means, it became normal. So 30 will cover you even the worst case. Now, if your real population is close to normal, or log normal or something like that, you can take less than 30. And you could explore that, remember, by taking a box plot or doing those normal probability plots or something like that. Or you could just say, hey, I've got infinite money, I'll just take my 30 samples and I know I'm in good shape. Or I don't know what I got yet. And that's what I'm doing next week while I'm out of town. I'm going to start out taking 30 samples because I don't know. And after that, and they were like, oh my God, 30. And I was like, well, after we learn, after we take some, after we look at it, maybe we can reduce it because we'll learn. And maybe it's more normal. We saw if it was normal, you can take one sample, right? But so that's part of your assumption. Okay, now population variances are unknown, but we're assuming they're equal. Okay, so this is the first. This case over here. So this is where we are right now. Numerical, independent samples. We're thinking about the mean, and we've said that those two guys are equal. So we're going to explore that one. Now let's see. All right, so here it is, the pool variance t-test. So what do you see? So it looks just like the t-test we've done before, right? We're coming up with a t-stat, and we're comparing our sample thing to our population thing, right? In this case, our thing is the mean. These are our sample. This is the difference between our sample means. This is the difference between our population means. Now, our null hypothesis is these two are equal, right? So this is a big fat 0. Now you'll notice when I put it into Excel for you, I went ahead and put a 0 in there, so you could remember, because otherwise you say, well, wait, what's mu1 and mu2? What? They're equal. Who cares? The difference of them is 0 in our hypothesis, but these are not because these come from a sample, right? What's this down here? This is your. Remember, you're always normalizing by your standard error. Your standard deviation divided by n. That's what this is, but it's not quite the standard deviation divided by n. No, it's because we've made up this pooled variance. We've got two samples now, but we've decided that the standard deviations are equal, or they're drawn from two populations that are similar, so we think they have the same standard deviations, and so we've put them together into this pooled variance. Okay, yeah. That's not all that amazing, is it? I mean, we've just kind of weighted them by the number of degrees of freedom, if you will, and then we've normalized it by that. So we're trying to kind of create a variance that's a combination of the two variances. All righty? And remember, when we do this t-test, we always have degrees of freedom. Remember, that was to account to give you greater variability. We made this wider, and that was to allow your confidence intervals to be broader, to reflect the fact that we have a little bit less understanding because, yeah, they're unknown, right? Our variance is unknown. That's why we got the whole t-distribution to begin with. Remember, the z was when we miraculously knew the variance or the standard deviation, and we could tighten up those confidence intervals just a little bit because we knew more. So remember, when we're going to look up a critical value of t, we have to have a number of degrees of freedom. Well, hey, big surprise, right? In the past, our number of degrees of freedom was n minus 1. Well, hey, we pulled them together. It's n1 minus 1 plus n2 minus 1. n1 plus n2 minus 2. Oh, yeah, that's not a surprise. I think that's what you would have done if you hadn't had any, oh, what did I do? I'm going to put these two together. Oh, yeah, okay. That's what I would have done. All right. So here's our t statistic. Remember, that's what we calculate to ask the question. Remember, we calculate that, and over here is going to be our t critical. And remember, we always compare the t stat or the s stat or the z statistic. Compare it to t critical. Alrighty. So t stat is our normalized difference away, and then we're going to have to get a t critical based on that. So let's see. Alrighty. And recall, if you don't want to compare it to this and compare it to t critical, remember we could calculate a probability. Instead of comparing it to a cutoff, we could calculate this probability out here and compare it to a limit if we wanted to. Or remember, we had the third way. You could calculate confidence interval and see where your confidence interval was. So you could, before we were asking, is the mean such and such, and we compared a t stat to a t critical, or we compared a probability to a probability level, or we compared a confidence interval. Now we can do that here too. So if you want to do that, instead of comparing it to a t critical, go ahead and you will compare this confidence interval, and you will see if it captures 0, right? Because we're asking the difference between mean 1 and mean 2. We've hypothesized that they're equal. So if the confidence interval includes 0, oh, well, they must be equal. And if it doesn't, if it sits way over here to the right or to the left of 0, well, they must not be equal at that confidence level, so reject it. So you can look at it that way too. And either way is statistically correct, statistically defendable. It's just whichever way you like to look at it. And when you do something like an ANOVA, for example, in Excel, it spits both of them out. As I recall, I haven't done one in a while, but it spits out a confidence interval, and it spits out the p-value too. So you can, whichever way you like to interpret it. Okay, I like the low p and get rid of it, or I like the confidence interval catching 0, however you want to think about it. So let's jump in and do an example, because it always solidifies things. And again, this example is going to show up in here in the next section too. And so watch it, because it'll help you learn. So hey, you're a financial analyst, and you've got 2 different stocks that are index stocks. One of them is tied to the New York Stock Exchange, one of them is tied to the NASDAQ. And you've taken some samples. Look, we took 21 here, 25 here. We got 2 different means, 2 different standard deviations. And so, assuming first that both populations are normal, we didn't take 30 samples, did we? We got close. And assuming that they have equal variances, why would we assume that? Well, they kind of look like it. They were both drawn from, U.S. stocks, so yeah, they probably are. They may be equal. So is there a difference between these two at our 5% confidence? Okay. So that's a good question. In our offhand look at them, well, that could be a difference, but they got, this has a little more variance. I don't know. So well, our assumptions fit, right? We've got equal variances, and they're drawn from independent samples. So we're over here. We're asking a question about the mean. We think it's equal variances. Let's use that pool T that we just learned. Besides, we haven't learned anything else. We might as well use it. Let's try it. So pool T. So again, our null hypothesis is the 2 means are equal. You can express it this way or express it this way, whichever you like. Our alternative hypothesis is they're not equal. And remember our rules. The null hypothesis always had an equal in it. The anti-null one, the never has an equal, and the hypotheses are always stated relative to population things, population parameters and not sample parameters. Okay, so let's calculate our t statistic. There's the mean from sample 1, the mean from sample 2. There's what I promised. We claim that they're equal, so that's a big 0. Here's this pooled S. Right, and here they calculated this guy down here. Remember, that was your weighted pooled variance, just plugging things in. There was your two numbers. There was your variance 1, your N2, variance 2. All right, there it is. There's our T stat. Okay, now we got to get a T critical to compare it to, or we can just use that and get a P, whichever way you want. So here, let's see what we do. All right, our alpha is 0.05. Where'd that come from? You picked it, right? You're going to make this statement 5% confidence. You didn't want 5%, 1%, okay, that's fine. You're choosing, or something's guiding you. 5's common. Degrees of freedom, N1 plus N2 minus 2 is 44. So our two critical values, Y2, oh, this is a two-tailed test, Y equal, right? It could be off on the bottom or off high. Okay, we're putting alpha over 2 on each side, so we can go to the T table and look up for a probability of 0.025 at 44 degrees of freedom. What are the critical values? There they are. So this is what we're going to compare our T statistic to. There it was from the other page. Okay, it's out here in the reject region. Okay, so what are we rejecting? We're rejecting our null hypothesis, our thought that the two means were equal. So therefore, our conclusion is there's evidence that there's a difference. And remember, you kind of don't say, well, I proved there's a difference. You know, this is statistics, everything's wiggle room and stuff. So yeah, so we concluded there's evidence of the difference in the means. It kind of looked like it, didn't it? Yeah, okay. And how did we conclude that? We did a statistical test, and we did it at, and you might even want to say there's an evidence of a difference in the means at a 5% confidence level or something. So you can, in your conclusion, you can be stating what alpha you used. So no different really. You can see how this is really not much different than what we did last week. But we've got two populations, and we're restating the problem sort of this way. You can see why I'd be like, well, you know, you could read this chapter and probably master it from what you knew before, but there are some nuances that makes it worth teaching. Okay, now, or if you don't want to compare it to a T critical, remember I said you can do confidence interval? Well, here's the confidence interval, right? There was your critical value. There's the number we calculated the pooled variance. There was a difference in the means. There's your critical value. There's that standard deviation, if you will. See, look, this confidence interval does not contain 0. Therefore, you think mu1 minus mu2 doesn't probably equal 0. That means they're not equal. So again, since 0 is not in the entire confidence interval, we can be 90% confident that that one, the New York Stock Exchange Index X Fund, had a bigger mean than the NASDAQ. Very simple, but again, very, very powerful conclusion, very defendable conclusion. You know, and you've gone through it in a methodical way. You've complied perhaps with the assumptions, the normality and things like that. So people are not going to be able to argue much with you, rather than just saying, well, they look like they're different, or the percent error is this, or something like that. You've got a statistically defensible way to make that conclusion. All right, so that was up here. We assumed these two guys were unknown, of course, but that they were equal. But now that may not be the case, right? Maybe we're comparing things from different, I mean, even in that case, perhaps they were different, because they were different funds, they were different index funds. So is there a test or an approach we can take when they're not equal? Well, yeah, and it's not, I don't think it's a giant leap of faith to see what you're doing when you flip-flop over here. Well, let's just not pool that variance together in that SP term like we did. Let's just treat them separately. Oh, okay, yeah, that makes sense. Why do we treat them separately? Because they're not assumed to be equal. They're different. Let's treat them differently. Okay? So that's what we're going to do. Again, the same assumptions apply, right? They're random and independent samples, and they're numerical too. Yeah, okay. We were from a normal distribution, or we had at least 30 samples, and the variances are unknown, and we cannot assume them to be equal. You know, this is the more general case, right? And so again, I also encourage you, if you get into a situation and you don't know, just like if we didn't know whether to use the z-test or not, we just use a t-test. It's more conservative. Here, well, this is more conservative. Yeah, you can always go that route. And, you know, hey, that's being safe, right? So what's the difference? Well, almost done, right? We still have a t-stat. We still have the sample means. We have the population means, which, again, our null hypothesis is going to be that they're equal, so that's a big fat zero again. But instead of that SP with the 1 over N1 squared, the weighted sort of pooled variance, we're just keeping them both, okay? And our degrees of freedom has got kind of an odd calculation, sort of based on their variances, but it comes out to being very similar to a N2 plus N1 minus 2. It's just a slight variation on it. And what you'll do, this will not come out even, and so just round it up, and that, so, because, I mean, well, I guess magically it can come out even every once in a while, in general it won't. So let's do what I love, let's work the same problem, very same problem, exact same problem, with this approach, because that way we'll see what the differences are. So same data, no difference, same number of samples, same mean, same standard deviation, but we're assuming they're normal with unequal variances. And we're asking the same question. Is there a difference between the mean at 5%? So now we're going to use our separate t-test. But still a t-test. Why is it a t-test? Because we don't know the variances, right? We assumed we didn't know the variance of the population, right? That's what we did, we knew the z-test, all right? So again, our null hypothesis, here's our sample, here's our t-stat, plugging in just the data straight from what we measured, 2.019. Here's our degrees of freedom. I didn't round it up, they rounded it down. Well, told you wrong, round it down. I think I rounded it up on mine. That'll just give you one more. Use the, yeah. So anyway, it didn't come out even. Use 40. I'll have to check that for you. I would thought you would have rounded it up. Okay, so here, where do we fall? Here's our t statistic. Okay, here's our two critical values at 40 degrees of freedom. So it barely fell on the other side. Barely fell. Okay, so our conclusion is there's no evidence of a difference in the means. Yeah. So we by taking this different approach, we arrived at a different conclusion. Now, should that bother us? No, it's statistics, right? And plus, yeah, like you're saying, it's right on the edge, right on the edge. It barely fell across the reject region. And with this one, because we assume separate variances, it's going to get, you know, it's going to give us a little more wiggle room. And so that's why we wound up not rejecting it here, I think. And so, and again, they were both close. Remember, the other one was pretty darn close to reject too. So this is close. But so you know, the moral of the story is, which would you use? Well, you're going to have to decide. Were these samples drawn from populations with equal variances or not? So if this were me and I had done this and didn't know and I did both, I would be sitting there saying, well, this one is close, you know, the other one was and the other one was further into the reject region. I'll probably more go with it, but it also might encourage me to take a few more samples, you know, if you can, to do a little further, you know. I would probably say, well, I'm going to reject it, reject my null hypothesis, say there's a difference, but I'd like to do some more tests, or take some more data. Yeah?
So why would you not just do it that way every time, since it's basically the same amount of work and then it's a more accurate?
I probably would, except the other one, you did gain a tiny bit more. When you assumed that they were equal, we were able to kick ourselves out here and reject it. You know, and this time we couldn't. You know, because you were, remember, your goal is kind of to prove, remember last time we said your goal was sort of you want to prove H1. You know, in this case, we're kind of wanting to show perhaps that there's a difference in the fund, so I can buy the one that does better. And so with the other test, with the other assumption that they were equal variances, you were able to say, oh yeah, there is a difference in the means. And this one you can't. So you get a little bit more information out of the other one, but at the risk of making an incorrect assumption. So you're right, I probably would always start with this one. Because if you started with this one and it fell in the reject, you're done. You're right? You know the other one's going to do that. So yeah, I probably would always start with this one. And again, because it's more general anyway. So I think it's a better choice.
They said to round up or round down to 40, but they actually used it for 41.
Did they?
Yeah, because if it was at 40, it would have been the exact same as your
See, I would have
critical
thought.
value in your test.
Yeah, see, I would have thought you rounded up too, because you always, the more degrees of freedom is the right direction to go.
At 40, it's 2.021, which is exactly what your critical value.
Yeah, and then, well, so that is the one for 40.
Yeah.
Yeah.
Well, but their test statistic is for 41. Their-
This one, no, with this one, that was just calculated from the, from the means and the,
Oh.
yeah, this is a critical value. So they used the one from 40? For 40, this number
Yes,
came from
they did
40?
use
Yeah,
that.
okay. Yeah, I would have thought you'd have gone up. I really have to check that. Let's, because that does, I would have thought you always went up. But a nuance, but it's an important nuance. Let's see. Yeah. Gotta pay attention for it. Yeah, you gotta pay attention to these little things. If you want to take the same practice that everyone else does, then obviously you can see I haven't done this one. So let's see what they say. I'm gonna have to read that because the book doesn't say either. Yeah, I'll have to read and check. If there is a way, there is a standard practice, if the standard practice is always to truncate it or to go up, that's a little bit of a difference. It would make a difference. Would it have failed if they used 41? What's this for 41?
2.0219.
So barely
It would have been right on that,
2.0219. So it would have moved it a tiny bit this way.
right? But at 40, it's 2.0195. So 02.
Yeah, so it moved it, 41 moved it just a little bit more this way. Yeah.
But 41 would make it fail. Or reject.
Yeah, still, it would still fail to reject, right? Because it would still be 2.02195, right? It moved it this way a little bit, is that? Yeah. Let's see.
It would be right on it, wouldn't it? It's 2.0195.
Yeah, so we had 2.0, yeah, so we're 195. Yeah, it would have been still, yeah, it would have been on the other side, wouldn't it? Yeah, you're right. It would have changed it. Yeah, I gotta check that. But again, here, this one's so close too. And we talked about that last week, if it's that close, you probably need to do some more. Yeah, we'll push it through away. Where I thought I rounded it up. I know I did homework, Bob. I know they did. I wonder. What if they committed for trying? I'll check that. I'll come back and let you know. All right. So now let's see. Now what happens? What happens if the populations are or your samples are related? So like we said, you did a before and after, or you had some other reason to relate some of the samples to one another. So let's see. We're kind of over here, maybe. We're not in the world where we're gonna. So we compare matched samples, or we can have repeated measures before or after. So what they're doing, if they match samples, they're going to use the difference between the matched samples. So this would be, the difference is the sample from sample I is, if we had 10 samples, say, so this is the third sample from before and after type thing. And so it eliminates variation among the subjects, like say if it was a drug test and you got these people before and after, so you compare that person to before and after, not just a whole mean of a group. Okay, it's again assumes we're normally distributed or we have a lot of samples. Now, let's see, I'll look at the test and then we'll talk about it. So just a subtle difference, instead of saying mu1 equal mu2, look, we're just going to form all these differences, alrighty, and then we're going to come up with a mean for the difference, mu d, and a standard deviation for the difference, where n is, of course, your total number of paired samples, and then n1 equals n2 if they're paired, right? And then we're going to just ask our same old question that we've always asked, our same t-stat, except we're just going to look at d, with n-1 degrees of freedom. So again, I think you would have come up with this, right? And we're going to use a t-test, and we're going to either have an upper tail or a lower tail. We're going to compare, or if they're equal. And if everything was equal, right, that we would assume that the differences would be 0. So we could do that and put alpha over 2 on each side. And again, it's n-1 degrees of freedom because it was n samples. So we're just going to look at the differences now. And we could also do a common sample. So there's almost no difference in this approach, except a subtle difference, right? Because we're matching the samples. We've got a little bit more knowledge, correct? Before, we took 21 samples, say, from the New York Stock Exchange, 25 from the NASDAQ, and we crammed them all together and got a mean and a variance. Well, here, we're going to say, this one is paired with that one, this one is paired with that one, so we're able to look at the difference, which will give us a little bit more knowledge, right? Slightly more. So let's do an example, and then we'll explore what we mean by that, so it'll make sense. So here's a good example. We've got these salespeople. Alrighty, that one must be me, right? There's my, of course, you got no complaints. Yeah, and so
0.
yeah, I like that too. And so they did it before, and this guy's great, and the after. And so you're asking yourself, did my training work? Did my number of complaints go down? Right offhand, looking at it, I would say, yeah, it looks like it. But we're going to ask ourselves this question in a statistical way with a certain percentage, and let's see. So, because it does look like everybody went down, and TF went down a bunch, but clearly TF in both cases is skewing it, right? This person is a bad salesman, and they're noxious, and they're getting a lot of complaints. And so if you could envision that there might statistically not be a difference in the two groups. So we can use the paired because they're related, right? This is the same person, this is the same person, so we can use this difference. So let's form the difference. There we did, the difference. And so now let's just do our statistical analysis on this alone, just the differences. So our D average is that. Okay, yeah, it's just that divided by 5, right? And our standard deviation on the differences is 5.67. So you can see how, well, with that big a standard deviation, you could assume that there isn't really any difference. So let's ask the question statistically and answer it statistically. So has the training made a difference at the 1% level? So our null hypothesis is that the difference is 0. There was no difference. The training made no difference at all. Our alternative hypothesis is that it did. 1% we've selected. Here was our average difference, and our standard deviation, we didn't write it down. Here's our test critical values. 0.005. Look how much bigger it is than, remember we're always using 0.025. This is considerably tighter. We're actually 1%. We had 4 degrees of freedom, right? Because we had five paired samples, so 5 minus 1. So and then our test statistic is the standard normalized difference of the sample from the population. That was 0. So that was our assumption. Standard deviation. There's our n. So our minus 1.66. Oh yeah, it's way in there. Okay. Yeah, it did look like a difference, didn't it? Let's see, right? No, I don't know. Let's see. Yeah, do not reject it. So there is not a significant change in number of complaints, but it did look like a difference, didn't it? So at this statistical level, there really wasn't a difference. So, you know, TF skewed it a lot, I think. You know, it's an interesting conclusion. I would have thought by looking at it, there was a difference. You know, but statistically, no, it fell in here. And I played with this one, because I thought, well, what, did they fool us again? Did they pick a low alpha? But no, because it's moving way out there. So you know, I tried to see what alpha you'd have to get before you grabbed it, and it's like, I don't know, 25 or 30%. I forget, it's a lot. So don't reject it. There's not a significant change in the number of complaints. Very interesting. I would have, you know, statistically, you wouldn't have thought that set of data told that.
So if you had done an outlier test and found TF was an outlier, and you redid the numbers, you would come up with the same answer? Or similar?
That's a good question. I think I'm gonna have to do it. I would say I would think you would, but I would have thought you would have come up with this one being statistically different too. So I'll do that. Yeah, we can do it all. Let's probably do it now on the Excel, right?
Your degree of freedom goes down.
It does. It does. And, you know, we've got a small sample. You know. But everybody improved except RK. Maybe he's the one that's skewing it. He didn't improve. Could improve. That's pretty funny. It's an interesting conclusion. I'd have to wrestle with that one. If I was a training manager, I'd have to wrestle with that one because I liked the results looked good.
So I guess I don't understand, because they improved by like 2/3.
They did.
So then how is it at a 0.01%?
I think it's because here your standard deviation is so big. Because think about it, if you started shrinking this, you know, down to 1, if you shrunk that down to 1, you multiply that by 5 and you fling it way out here. And so your variability is so high, and and you didn't get much help. If you had a big number of samples, like I said, it's a small sample. If you had 100 people in your test, then that would shrink it down too, and it'd make this big, and you'd reject, and you'd say, oh yeah, there truly was a difference. So small sample, high variability. You just can't make that conclusion. Is what it amounts to. That's really what you learned from this example, I think. You know, I only had 5 salespeople. I had quite a bit of variability, and this person really didn't do anything to the study except add you a degree of freedom because they couldn't improve, and so really had a pretty small sample, and so that's what got you. So it's really, you're just saying, it's just such a small sample, I can't really conclude that it was a good training course or not. Although it looks like it. And so again, I think your conclusion, your real managerial conclusion is, well, I still think it looks decent. Everybody improved, didn't they? So you might be able to go back and say, well, look, I had too small a sample to statistically conclude it. Let me test it on more people. Let me train a few more and see.
Are we assuming the population from which we're getting complaints from is equal before and after?
Yes, we are. That's right. Because that would completely goof it up. You're right. They didn't say that, but I'm glad you brought that up because you're right. That's hard to control for, isn't it? Because you know they didn't go back to the same people and say, so in reality, that would come out in your design of experiments.
You've also got different salespersons who would potentially make different levels of sales, right?
Yes,
So maybe
yeah, you're right.
Anyway.
Yeah, you're right. See, they haven't normalized for that either. It's just total number of complaints. Maybe he's got 20 complaints because he has 10 times the sales volume or something. You're making that assumption too. And so you're right, there's a lot of assumptions in this data. And so really, if you control for those kind of things, you might come to a different conclusion. Yeah, if you normalize these numbers to the amount of business they did, so because I expect him to get 20 complaints if he did 10 times the amount of business. He was just real fast. Yeah, and this guy got no complaints because he sat there and drank coffee all day and did nothing. I mean, seriously, you can't. You got to control for that, and that is one of the things the design of experiments will talk about. That's not the best example, is it? And so, yeah, so since this is not the best example, let's look at the one in the book. Yeah, because we can. The one in the book, and I liked it, and that's why, again, just like the figure, I wanted to call your attention to it, because what it is, it's, oh, well, this is me actually doing that, training example. I actually did it, so we can play with it a little bit, but I don't want to do that. Let's see. It's the wrong Excel, but I did do it in there, so we could play with it later. I will, but I won't do it in the middle of class. So here. Yeah, okay, so here's, if you will, the example in the book. So this is example 10.1 and 10.2. So 10.1 is on page 347, 10.2 is on page 359. And what it is, here's the thing. It's pizza delivery. And there's a local pizza shop and a chain, and you're experimenting, and you want to see, is there a difference between the delivery times? So your first experiment you did, you just ordered 10 pizzas from the local guy and wrote down the times. Your second experiment you did, or the same part of this experiment, your second test, you ordered 10 pizzas from the chain and wrote down the delivery times. Now you can see you're getting exactly what your question is. You're screwing up if you're not careful, right? Because what if I order always from the chain at dinner time or rush hour, the traffic's bad, or they've got 50 orders ahead of them at dinner time, and vice versa from the local guy, I always order at 3 o'clock or 3 a.m. and there's no pizzas and they come in 5 minutes. So you haven't controlled for that. So if you treat this together with this pooled variance over here, assuming that their standard deviations are equal, which may not be the case because of how you ordered it, and to go through the same test, the same statistical analysis that we did with that simple approach, and ask yourself, is there a difference in the mean delivery time? So there's the mean for each one of them, the chain's more, there's the standard deviation. Is there a difference at the 0.5 level? I made your calculation of your critical value and your test statistics. In fact, I got your Excels here. The decision is no, there's no difference in the means. Okay, even though they were close, but you concluded no, you can order from either one. Pretty much your delivery time's the same. Okay, now let's make one subtle change in how we do our data. Let's not just order